mean, almost. It was just a matter of months, I think. The first guy to actually prove it, that there were some things that could not be solved, was the guy Church, a mathematical logician, American. And then Church, and then Turing came out with his Turing machine model of computation, and quickly showed that Church's model of computation and his, Turing's, were equivalent. Okay, and then the Church-Turing thesis effectively says that anything that can be computed by a Turing machine, or if you like, Church's lambda calculus, which is an alternative model of computation. Since they're all equivalent, whatever that you can compute can be computed on a Turing machine, because the Turing machine is just one of many models, but they're all equivalent, so you could pick virtually any one. But the popular one is Turing because it's so sort of visualizable and simple. Basically, it's just a simple machine with a read-write head and a tape and a set of rules on how to read and write the tape and move. It's conceptually so simple. Right? So talk about right. So in the previous chapter, let's see. So we talked about the Turing machine (TM) as a model with general purpose computer, right? And the Church-Turing thesis says anything that you can compute can be computed on a Turing machine. That now you can't really prove that. It's more, what is this? Calling it a statement of faith is a bit too strong, because there haven't been any counter examples yet. People don't think there will ever be one, because there's just so much experience and so many types of computing have been shown already to be equivalent to Turing machine, that it's a kind of generalization, if you like, that anything you can compute can be computed on a Turing machine. That's the thesis, Church-Turing thesis, which was never actually concretely, explicitly spelt out in Sipser's text, which is annoying. Had to get it from other text, but it makes sense anyway. So. We made, from previous chapters, summarizing a little bit, we made the rather vague notion of an algorithm, like a step-by-step series of actions to achieve some goal. That's the vague, general conception of what an algorithm is. But we made it much more precise by equating, effectively, an algorithm as a Turing algorithm. In other words, that step-by-step procedure, that list of actions that you go through, as executed by a Turing machine. So so now, when we think of algorithm, just think of Turing algorithm, or you can just equate an algorithm now with a Turing machine, effectively, because what's the Turing machine doing? Well, whatever it's doing, that you define, you label as an algorithm. Okay, so an algorithm is a Turing machine, effectively. So that's what it's saying this. And so anything that can be computed, there's an algorithm for it. Why? Because there's a Turing machine that can execute that algorithm. And since Turing machines, via the Church-Turing thesis, says anything that can be computed by a Turing machine, that means anything computable, there's an algorithm for it. You can deduce that modus ponens via the Church-Turing thesis. Hope you follow that. Okay, that's a bit of summary from previous chapter, some basic ideas there. Now we move on. So in this chapter we start looking at the power of algorithms to solve problems from two sides. What can be solved and what cannot be solved. And that's what's so famous about the halting problem as a classic example of what cannot be solved. Right? So the emphasis on this chapter is looking at a category of problems that can be solved and another category of problems that cannot be solved. And I said earlier, earlier sessions, this categorization, like separating, filtering problems that can be solved and cannot be solved, is an industry now. I mean, there's a huge number of researchers now working on this problem, to taking particular problems and see if they can prove that a particular problem is of the solvable type or the unsolvable type. Because it's important to know, right? Because if, well, we'll be talking about it in the next square in this session. It's important to know whether a problem is solvable or unsolvable, for reasons I'll get to in a minute, in a couple of minutes. All right. Okay. So in this lecture, these next few boards, only 18 pages, so we'll only be a few boards. We'll get through it fairly quickly. So we'll show that some problems can be solved using an algorithm, and others can't. Yeah? That's the theme. That's the main idea of this whole lecture 4 on decidability. Right? So we're going to explore the limits, the limitations of algorithmic solvability. How far can you go using algorithms to solve problems? Are there always algorithms to solve every kind of problem? No, indeed not. Some problems are just simply unsolvable. There is just no algorithm, and you can prove this. There is just no algorithm to solve certain types of problems, right? And that's the big lesson of this chapter, this lecture. Not this board, but it's coming soon. All right. Now, here's a comment here from Sipser, sort of interesting. Now, if this idea of unsolvability, or I'll be a bit more technical, undecidability, but we'll get to that later. Undecidability. If this idea of some problems just being unsolvable, that there's just no algorithm to solve them, if that idea sort of shocks you, because it's a kind of cognitive dissonance, sort of like going up to a priest and saying, there's no God, something like that. So going up to a computer scientist, let's say an undergrad, and saying, look, there are some problems for which there's no algorithm to solve them. Those problems are unsolvable. That can be shocking to someone who's sort of spent all their young life thinking computers can do anything. Okay, so the unsolvability of some problems that may come as a shock to some people. Right? That's sort of interesting comment here. Now, I mentioned I'd get onto this fairly soon. So, what's the point? Why study unsolvability? Isn't that sort of counterproductive? Isn't it? I mean, you have if you're a computer scientist, a programmer or something, and maybe it's your job, and your job is to solve problems.